Hello, this is FlippedHarber for Precalculus. In this video we'll cover section 5.3, Properties of Trigonometric Functions. Our objectives for this lesson are to determine the domain and range of the trigonometric functions, determine the period of the trigonometric functions, determine the sign of the trig functions, find the value of trig functions utilizing the fundamental identities, and then we'll use even and odd properties to find the exact value of trigonometric functions. Our outline for this video will start by talking about the domain and range, then we'll move on to the period. We'll talk about some periodic properties. We'll talk about the signs of the trig functions. We'll talk about some fundamental identities, move on to some even and odd properties, and then we'll take a look at some examples. Now, the domain and range of the trig functions, I guess there's no better way to talk about it than just to start telling you what the domain and range are. The sine and the cosine functions, that is the sine of theta equals A and the cosine of theta equals B, have the same domain and range. They're very similar looking functions. They both have a domain of all real values. We can take the sine of absolutely any angle. We can take the sine of all the positive angles, all the negative angles. We can take the sine of 0. So the domain is all real numbers. And the same is true for the cosine. The range, though, is very, very limited. The sine and cosine wave back and forth between a positive and a negative 1. And that is inclusive, meaning that you can actually get out a negative 1 and you can get out a positive 1. So our range for both the sine and cosine is all the numbers between negative 1 and 1. Now, the tangent function, if we stop and think about this as a fraction, where it's a over b, because the sine of theta is a, the cosine of theta is b, we can't have 0 on the bottom of that fraction. So anything that would give us 0 on the bottom of that fraction, we just can't have. So if you stop and think about this, the cosine of pi over 2 is 0. So that means that we can't take the tangent of pi over 2. And the same thing with 3 pi over 2, 5 pi over 2, so on and so forth. Notice it's the odd numbers on the top of those fractions. Our range, well, actually, it's kind of the opposite. There's no limitations on what we can plug into sine and cosine, but very limited on what we can get out. Here, we're somewhat limited on what we can put in, but we will get out any real number. We can get out negative numbers, we can get out positive numbers, we can get out 0. So our range is all real numbers. The cosecant, the secant, and the cotangent are kind of similar to tangent because they can all be thought of as a fraction. So we can't plug anything in that might give 0 on the bottom of that fraction. So for the cosecant, which is 1 over a, that is 1 over the sine, we can't plug anything in that might give us 0 for the sine. Things like 0, pi, 2 pi, 3 pi, and so on and so forth. For secant, because it's 1 over the cosine, we can't plug in pi over 2, 3 pi over 2, 5 pi over 2. And then for cotangent, it's sine over cosine. So again, the things that we can't plug in where sine is 0. Now, cosecant and secant are very limited on their range. It can be less than or equal to negative 1. That means that you can get numbers like negative 2, negative 3, negative 4.5. You can get numbers bigger than 1, 1.1, 1.2, 2, 5, whatever. But you can't get any numbers between 1 and negative 1. The cotangent, a lot like the tangent, we can get any number we want out. So its range is all real numbers. Now, when we talk about the period of a trig function, we're talking about how often it repeats. So all of these trig functions repeat. They just keep on going over and over and over and over. If we're talking about the sine and cosine, it's this wave pattern that just keeps on going on and on, waving on and on forever. Now, the sine and cosine repeat after 2 pi. Now stop and think about this. 2 pi represents once all the way around the circle. So the fact that it repeats, if we keep on going around the circle, that kind of makes sense, hopefully. So we say that the sine of theta plus 2 pi k is equal to sine theta. Basically, that 2 pi k just means that we've gone around the circle. Now, k is any integer positive or negative. Same thing with cosine. If we add 2 pi times some integer, we're going to get the exact same value. So that 2 pi k really doesn't do anything for us. It just sends us more and more times around the circle. Now, the cosecant and the secant functions also repeat after 2 pi, just like sine and cosine do. So that plus 2 pi k inside the cosecant and the secant really don't do anything for us. Again, k is some positive or negative integer. But the tangent and the cotangent functions repeat after only pi. So they've got a half of the period. They actually start repeating sooner. So we get rid of that 2 in there. So the tangent of theta plus pi k is equal to the tangent of theta. If we go halfway around the circle, it starts repeating. So here are those periodic properties all in one big table for you. You've got the sine of theta plus 2 pi k. Well, that's equal to sine theta. Same thing for cosine, same thing for cosecant, same thing for secant. But you'll notice in that last column, the tangent and the cotangent, we just add pi k. Now, the signs of the trig functions, this is a pretty important idea actually, is being able to locate where the sine, the cosine, the cosecant, the secant, tangent, cotangent, where they're positive, where they're negative. And we see that in the first quadrant, in that upper right-hand corner, all of the trig functions are positive. In that upper left-hand corner, only the sine and cosine are positive. Oh, excuse me, that table is actually wrong. That should say that the sine and the cosecant are positive. I didn't even make this. I copied this off the internet, so you can't believe everything you read on the internet. So that's actually wrong. Up there in the upper upper left-hand corner, that should say sine and cosecant are positive. Down in the lower left, tangent and cotangent are positive again, and then over in the lower right, cosine and secant are positive. Alright, so I'm going to have to make my own image, I guess, for the next time. But moving on, we're going to talk about some fundamental identities. Now, you're going to get kind of sick of the whole identities idea in the next chapter, but a trig identity is just an equation that relates two or more trigonometric functions. Now, basically, a trig identity always works as long as you can actually plug in that value. So remember, you can only plug certain values in for tangent. So if you've got a trig identity with tangent, right away it's got that limitation that you're not going to try to plug in one of those numbers. Okay, so we're going to take a look at some reciprocal identities first. Now, reciprocal is just basically a fraction. The cosecant is 1 over sine. Okay, no big surprise there. You probably should have figured that out by now. The secant is 1 over the cosine, and the cotangent is 1 over the tangent. So those are referred to as our reciprocal identities. Now we have some quotient identities, again very closely related to these reciprocal identities. The tangent is equal to the sine over cosine, and since the cotangent is the reciprocal, it's equal to cosine over sine. Now, our next ones that I want to talk about, very, very important ones, it's a group of identities that are quite often referred to as the Pythagorean identities. So I just wanted to throw this picture up here. I want you to remember on the unit circle, that hypotenuse of that triangle is 1. So we can set up the Pythagorean identity for this triangle, and just remember that that hypotenuse is 1. So what we can do is take our sine theta and square it, plus our cosine squared, and what we get is that hypotenuse squared. Well, 1 squared is 1. So this is actually a Pythagorean identity where we're taking the two legs of that triangle, the sine and the cosine, squaring them, adding them up, it equals the hypotenuse squared. The hypotenuse is 1, the hypotenuse squared is also 1. Very, very important identity. You're going to use this one a whole lot. Now, if we make some fancy little changes to that basic Pythagorean identity, we get other ones, like this one. Really, the way that we get this one is we divide all three terms by cosine squared. If you take sine squared and divide by cosine squared, you get a tangent squared. Cosine squared divided by cosine squared is 1, and then 1 over cosine squared is secant squared. So you take the top Pythagorean identity, divide by cosine squared, and this is what you get. Well, if you're going to divide by cosine squared, you might as well divide by sine squared also, and this is what you get. 1 plus the cotangent squared theta equals the cosecant squared theta. Okay. Again, this group is what we refer to as the Pythagorean identities, because really it's just Pythagorean's theorem being applied. Now let's talk about some even and odd properties. Now you remember that an even function is a function that is that can be reflected over the y-axis. An odd function is one that is symmetric over the origin. That means that things in the upper right are reflected down to the lower left. Well, even functions, not only are they symmetric over the y-axis, but if we plug a negative into our x, well, that negative just basically goes away. Odd functions, not only are they symmetric over the origin, if we plug that negative in with that x, that negative will move out in front of the function. So it turns out that our trig functions are basically even or they are odd. There are no trig functions that aren't one of those two. They've got to be even or they've got to be odd. It turns out that the sine is what we refer to as an odd function. The cosine is an even one. The tangent is an odd function as well. The cosecant is odd. The secant is even, and the cotangent is odd. So actually, let me put it this way. They are all odd except for cosine and secant. Those two functions are even. Now, let's talk about some examples. They want us to find the exact value of the sine of 390 degrees without using our calculator. That means that we need to look at our trig table. You should have started filling that out already. And let's face it, by now it should probably all be filled out. So how in the world are we going to use what we've just talked about in this video to find the exact value of the sine of 390 degrees? Well, what we're going to do is just realize that the 390 degrees is once around the circle, 360 degrees, plus another 30 degrees. So we just found out that there's this periodic behavior with trig functions, and all I need to do is find the sine of 30 degrees, which is 1/2. Okay. Now, here's a big one. Sounds like a lot of work, but it's actually not that bad. The sine theta, they're telling us, is equal to negative square root of 5 over 5. The cosine theta is equal to negative 2 square root of 5 over 5. What they want us to do is find all of the other four trig functions. They want us to find the tangent, the cosecant, the secant, and the cotangent. And we can do this just by using our reciprocal and our quotient identities. So let's start by just finding the tangent. The tangent is equal to the sine over the cosine. So we take negative square root of 5 over 5 over negative 2 square root of 5 over 5. Well, we get a 1/2. So hey, we got 1 out of the 4 done. All we got to do now is use our reciprocal identities to find the other 3. All we do, flip the negative square root of 5 over 5, and we'll have cosecant. Flip the negative 2 square root of 5 over 5, we've got secant, and flip the 1/2, and we've got cotangent. So really not that bad at all, just by using our reciprocal and our quotient identities. Okay, so now it's time for you to try some of these on your own. I'll see you in class, and I'll see you online.